Welcome everybody, it's Dave here. In this video we're going to talk about chapter 1.1 from your textbook titled The Basics of Functions. So our goal really is to learn about calculus, and functions serve as the foundation of all of calculus. So what I've done is I've divided the video up into three parts. In part one we're going to talk about what a function actually is, and we're going to look at four things: what domain means and how to find it, how to evaluate functions, how to graph them, and how to solve, how to look at some properties of functions. In part two, we're going to see a different type of function called a piecewise function. We'll explain what that means. And in part three, we're going to talk about some word problems. So I'll see you on the other slide. All right, so our first step is to actually define what a function is. And I have the main definition written here, but I'm actually going to describe it with this picture with a conveyor belt and kind of a little machine in the middle. So what I want you to imagine is taking a number. So you just pick a number, you put it on the left side of the conveyor belt. So say you take the number 2. We put it on that conveyor belt, it takes it into the machine, and the machine kind of does something with it, and then it spits something out. So let's say it spits out the number 4, for example. Okay, so something happened to the input, and we got a corresponding output. Now suppose we put in a different number. Say we put in the number 3, that goes into the machine, it chews it up, it spits it out, and we get out the number, say 9. Okay, and we can keep doing this. Let's say we put in a 5. Clearly I'm going for a pattern here. It spits out the number 25. So clearly every number you put in, I'm squaring it, so I'm getting the square of it on the other side. But needless to say, what's happening is we're taking an input and we're getting a corresponding output. What's happening is the thing in the middle is what we're going to end up calling a function. So let's look at the definition. The definition says you have two sets, D and R, and the function takes something from D and brings it to R. So it takes your input from D, that's like a set of numbers, and it gives you an output in this other set, R. What the function is it's a rule that assigns to every x that you put in from the domain, from D, which we'll call the domain, it assigns one and only one element, one output, y, call it y, in the range R. So we'll go back up to our picture here. Now we're not putting in a specific number, we're putting in a variable x. It could be anything. And the x slides in, the function chews it up, and out spits one output that we're going to call f of x. So the thing that lives in the middle, this little machine in the middle, is your function f. It takes that input x and gives you an output f of x. The real key point here, and we're going to come back to this, but the real key point is that it assigns one and only one element. For every input, you're only going to get one thing coming out of the machine. You can't put in an x and get 5 other things that come out the other side. You can only get one. All right. Now there's some more terminology that we're going to need to be familiar with. The x, the input, is called your independent variable, and I'm going to write these on the screen here in a second. It's independent because that's the thing that starts it all. It's not dependent on anything. We're going to just put that variable in. That's the beginning. The y is called the dependent variable, and the notation we use is that y is equal to f and in parentheses x. It signifies that the x is your input, the y is your output, and the y is what we call the dependent variable because it depends on the independent variable x. So we have independent variables, dependent variables. D, the set of all possible inputs, is called your domain, and R, the set of all possible outputs, is called your range. So I'm going to put those definitions here. And you can see those definitions there on the screen. So what we're going to do next is specifically look at the domain of a function. Now the domain is, as we said in the last slide, the set of all possible inputs for a function f of x. And I'm going to highlight the three words here, all possible inputs. And the key word is possible. So sometimes there are inputs that we can't put into a function, and we're going to talk about that here. When I give you a function f of x, generally there'll be some rule. So it might be, f of x equal to x squared. That's my favorite function. And so the x is your input, and the question would be, well, what values of x could I actually put into this function? And the answer would be anything. It doesn't matter. If you give me 0, I can put 0 here. If you give me -1, I can put -1 in here. It doesn't actually matter what number you give me. So that's a very friendly function per se. But there are other functions that have perhaps some issues. For example, 1 over x. That's a pretty good function, except for the value 0, because if I put in 0, we will have 0 in the denominator, and then it's not happy. So the domain of this function is all real numbers, all numbers, except for 0. And another example is a square root. Suppose I give you the function, the square root of x. Again, you can put a lot of numbers in there and it'll be okay, but you can't put a negative number in this because we cannot take a square root of a negative number. So the domain is all positive real numbers. How do we do that? How do we express this? Well, with our domain, if the domain D is all real numbers, we're going to use this fancy R. This fancy R just means all real numbers. Okay. Another way that we can write it is as an interval from -infinity to infinity. For the next example, the domain is all real numbers except for 0. So what you'll do is you express this as two intervals. We express it as the interval from -infinity to 0, and then the interval from 0 to infinity. All open parentheses on these, and then we put this big capital U, which stands for union. So that'll represent the domain, and it essentially tells us everything except 0. And then the domain for this is going to be everything from 0 to infinity, and I can include 0 because 0 is okay. So I'm going to use a square bracket there. So we're actually going to use intervals to express our domains, and you can get some practice with this. Just as a quick final example, so the two things you need to be careful with are denominators and square roots. But for example, I might give you a function that looks like this: the square root of x plus 5 over x, let's say x plus 2. Okay. Now, this function has both a denominator and a square root, so if I asked you for the domain, you're going to need to figure out how to find that. So I'm going to look at two parts of the function. The first part is the square root part. This will only be happy if x plus 5 is bigger than or equal to 0, because we need the inner part to be non-negative. And therefore, you could solve this inequality. X has to be bigger than or equal to -5. So I'm going to circle that. That's the first condition that we need to have satisfied. The next condition, x plus 2. Well, I know that x can be anything except for -2, because I don't want x plus 2. I need x plus 2 not to be 0. So this would mean x cannot be -2, and that's the only other condition that needs to be satisfied for this function. So for the domain, we have to express this as an interval. And one trick that I like to use is to actually draw this on a number line. So I'm going to put some numbers here, -5, it'll go to -2, and the red condition says, okay, well, it has to be bigger than or equal to -5. So it's going to start there and it's going to go this way. The blue condition says, uh-oh, you can't be -2, so I'm going to put a circle there. And then both of them say, well, and then the red says, well, it can keep going. So the blue is very happy as long as it's not -2, and then red has to be bigger than or equal to -5. To express this domain, we're going to express the interval from -5 to -2, and then so that's going to actually be a square bracket because -5 can be included. Then open parenthesis, and then we're going to union, so we put that big U with -2 to infinity. And you always put a parenthesis on the infinity. So the domain would be expressed in this way. All right, and you can get some practice with this, but the main things I want you to keep an eye out for are denominators and square root. Functions can also be graphed. It's a great tool for us to be able to graph a function, and generally you'll be given a function y equals f of x, and we can graph that on an xy plane where x, your independent variable, is here, and y, the dependent variable, is there. And you guys probably have had some experience graphing, but essentially for every x there is a corresponding y, so you'll have a bunch of these things called ordered pairs. And if you plotted all of the ordered pairs for any value of x that you picked, you might get a nice curve, or any shape really, and that'll represent your function. The only requirement here to be a function is that every input, so remember if you take an input x, you can only have one output y. So there can only be one y value associated with every x value. So when you actually graph a function, there's this test called the vertical line test that helps us determine if it's a function or not. And here's what the test says. It says that a graph is the graph of a function if every vertical line that you can put on the graph intersects it at most one point. This ensures that every input only has one output. So for example, if I drew you a picture and I said, oh, here's a function, it's like, it goes like this and then it goes off like that. This is not a function because there are some vertical lines. I'm going to draw a vertical line here in green, let's say. Let's use purple. There's a vertical line here that actually passes through the graph at 1, 2, 3 points. So the input x at that purple line has 3 outputs, and that can't happen for a function. So the vertical line helps us determine if a function is a function or not. The next step is to understand how to actually evaluate a function. So we'll be given the rule in terms of an x will be our variable, and suppose you're given this rule for the function and we want to evaluate the following terms. So let's go through kind of how to do this. What I'm going to use is a red pen to mark what the input is. So if x is the input, you're going to want to understand where x is in this function. And so for part A, we're looking for f of 1, and that means that anywhere there's an x, I'm going to replace it with a 1. So what it's going to look like is 1 squared plus 2 times 1 plus 1. And I write it 2, plus 1. And so if you evaluate this, you'll get the number 4. So f of 1 is actually equal to 4. Now we can do the same thing over here in part B. In the first part, you're going to replace x with a minus 2, and then you're going to replace x with a 3, and then we're going to take the difference of the 2. What I really recommend for you guys is to use a lot of parentheses. So I'm going to put parentheses around this term and around this term so that I can really isolate exactly what each term is before I find the final answer. So if I put in minus 2 to the function, you're going to get minus 2 squared. You do have to square the whole negative 2, plus 2 times minus 2 plus 1. And for f of 3, we're going to get 3 squared plus 2 times 3 plus 1. And now you can evaluate these. Of course, to evaluate it, you want to use the order of operations. And so you simplify what's in the parentheses first, and then you take that final difference at the end to get an answer of negative 15. Part C looks a little funny because I'm asking you to evaluate f of some triangle. And this is just to really drive home that input, whatever the input is that you see here, is going to replace the x from the function. So it'll actually be triangle squared plus 2 times triangle plus 1. I don't know what triangle is, so this would be my final answer. This really is to just emphasize that I can put anything inside of that evaluation parenthesis for the function. So in part D, if I want f of a plus h, the a plus h really serves the purpose of the triangle from part C. So if you were to evaluate this, you're going to take a plus h and put it where the x's were. So it'll look exactly like this. Okay, and we can just leave it like that. We don't need to expand it anymore. So this would be my final answer for f of a plus h. This is going to have a lot of importance when we look at calculus later in the class. For part E, suppose I want the difference of f of a plus h minus f of a. Well, what that's going to look like, f of a plus h, we already found from part D. That's a plus h squared plus 2 times a plus h plus 1. That's the first part. And then I'm going to subtract f of a. And a would just be putting in the a squared plus 2a plus 1. Now in this instance, I actually do want to simplify this and see kind of how it all is going to play out, what it actually reduces to. So I'm going to zoom up a little here, and let's expand out, using our algebra techniques, let's expand out all of these terms. So I'm going to use some colors. A plus h squared, if you actually expand that out, you'll get a squared plus 2ah plus h squared. And you guys can look up the details there. 2 times a plus h, remember we're going to use the distributive property here. That's 2a plus 2h. And you still have that plus 1. Now for the second set of parentheses, this minus sign is going to apply to every one of these terms. So I'm going to distribute in the minus. That's minus a squared minus 2a minus 1. All right. And finally, these parentheses that I've drawn in here, they actually aren't doing anything, so I'm going to eliminate those. And we can combine like terms. You're going to notice a lot of stuff cancels. So this a squared is going to cancel with that a squared, the 2a with this 2a, and the 1 with this 1. So ultimately, you're left with 2ah plus h squared plus 2h. And that would be for part E. All right. And part F is the same as part E, but it actually has us divide by h. So from part E, I know that the numerator is 2ah plus h squared plus 2h. And that's all going to be divided by h in this example. And the reason why I'm showing you this is the last step. We want to simplify this a little more. You can factor out an h from the numerator. So we're going to look at the numerator here. And you're going to factor out an h from every term. So you'll get 2a plus h plus 2. And that'll all be divided by h. And the reason why we do that is that I can now cancel an h. So your final answer here is 2a plus h plus 2. So you might look at these examples and say, these seem so random. Well, this example that we did right here, this is going to be called the difference quotient, and it's going to be fundamental in studying calculus. So you'll see this very, very shortly, and that's why we're doing it here. Similar to the last slide, I want to do one more example with a different function. So our function here is going to be 1 over x plus 2. And again, I want you to highlight what that input is. That's where the input will go. So in this first example in part A, we want to find f of minus 1 times f of 0. So f of minus 1, that's going to be where I take the function and I put an input of minus 1 where there was an x. And f of 0, you're going to take the function and you're going to put an input of 0 where x used to be. And these are multiplied together. So ultimately in blue, you'll get 1 over 1, and in green, you'll get 1 over 2. So the answer is just 1/2. Okay. In part B, we'll do the same thing. So again, my input's minus 2. So you're going to put a minus 2 in where you see an x. And what's going to happen here is you'll actually see that this is 1 over 0. And this is a frown face. This is no good, obviously. This is not defined. And the reason is that minus 2, so I'm going to put a big warning sign, minus 2 is actually not in the domain of this function that we have defined here. All right, so it actually wasn't proper for us to ask what that value is because it was not in the domain. Okay. And then finally for part C, I'm going to compute that difference quotient like we did on the last slide, but we're going to do it all at once here. So it's going to look a little messy, but we have divided by h, and I'm going to use colors again. So f of a plus h, we're going to take our function, and instead of an x, we're going to put an a plus h, but you still have the plus 2. So again, I'm just replacing that red underlined x. Then I'll do f of a, so this is going to be minus f of a, so instead of x, you're going to put an a, and it'll look like this. So this is the unsimplified answer for this difference quotient. But if I do want to simplify, you're going to have to combine the fractions in the numerator. So you'll still have this over h, but in the numerator, we have two fractions and we're taking a difference of them. The quickest way to do this is to actually take, it's a little trick, start with the numerator on the first fraction, multiplied by the denominator of the second fraction. So we're going to put that up here. 1 times a plus 2. Now this is a minus sign, so we're going to write minus. Then take the numerator of the second fraction and multiply by the denominator of the first. So it would be 1 times a plus h plus 2. And all of that gets divided by the product of the two denominators. So it's this denominator times that denominator. Now at this point, what you have is really two fractions that are divided by one another. So you have the top fraction way up here and the bottom fraction h over 1. So what you're going to have to do is simplify that top fraction as much as you can, and then we're going to deal with the dividing the two fractions. But if I simplify the top fraction, I want to distribute this minus 1 into these terms, and then cancel what I can. So what you'll have, here's the main fraction, what you have is a plus 2 minus a minus h minus 2 after distributing. And in the denominator, I'm going to leave that unsimplified. So we have that as our fraction, and that's all over h over 1. Notice the a's cancel, and the 2's will cancel. So in the numerator, you'll have minus h all over a plus h plus 2 times a plus 2, and that's divided by h over 1. So the final step, I'm going to zoom up here, the final step is because we're dividing fractions, we have to multiply by the reciprocal of the denominator. So that this top fraction stays the way it is, so we don't have to modify that at all. And instead of dividing, we're going to multiply by the reciprocal of the bottom fraction. So we flip that over, 1 over h. And what will happen is we're going to multiply straight across. You multiply this across, and you multiply this across. And the h's are actually going to be able to cancel. So ultimately, you're left with 1 over a, and then a plus h plus 2, and a plus 2 as your final answer. The next stop on our journey about introduction to functions involves properties of functions. So there's 4 that we're going to need to know. The first is what it means for a function to be increasing. All that this means is that the function f of x goes up in some way. So any function that you can draw that has an upward trend to it is an increasing function. For decreasing, you can probably guess what I'm going to say, and that's any function that would be decreasing. So this would be f of x going down. Now, in terms of concavity, this has to do with the shape of the graph. So when we say that a graph is concave up, what we mean is that the graph looks like a cup. So it'll have either a shape like that, like the left side of a cup, or a shape like that, which looks like the right side of a cup. So it's kind of like a smile. In terms of concave down, the best way to remember this is that it looks like a frown. And that would be either the left side of a frown or the right side of a frown. So it resembles the shape of a frown. And functions that have that shape are said to be either concave up or concave down. And we'll deal with this a lot more later in the course, but this is your first introduction to it. The final property that I'm going to highlight is what we call a continuous function. So I've given you the real definition here, and that is that a function is said to be continuous on some interval if the graph does not have any breaks, gaps, or holes. So let me draw you an example of a really nice function that is continuous. It would just be a graph that doesn't have any issues as we draw it. Nice, smooth, doesn't have to look like this, but this is a perfect continuous graph. Whereas another function I could draw might look like this, and then it might have a hole there where I don't have a domain. It could have a break where you might stop here and then resume up in that direction, or it might even just shoot on up to infinity and have what we call an asymptote. So it follows this line all the way up to infinity. Those things are not continuous. The black one that I've drawn is. A function we say is discontinuous at a point if the graph has a break or a gap at that point. So this point right here would be a point of discontinuity. That's how we would describe it. This point here would be a point of discontinuity, and this point here, this x value down here, would also be a point of discontinuity for the graph. Again, this is your first introduction. We're going to see this a lot later in the course. The second part of this lecture video is going to focus on piecewise functions. And these functions are really just functions that are defined in parts. So think of it as in pieces. That's where the connotation comes from. So that they're defined differently on different parts of their domain. And one example is given here. And you'll normally see this curly brace here, and you'll have different conditions for which you'll follow a different rule. So what this is saying is that you should follow this rule if your input is bigger than or equal to 0, and you should follow this rule if your input is less than 0. So as an example, if I said f of 5, well, 5 is bigger than 0, so we're going to follow the blue rule, and therefore it's just going to be equal to 5. If I asked you to find f of minus 7, well, minus 7 is less than 0, so we're going to follow the green rule. And the green rule is going to tell us that we need to take negative times the input. The input's minus 7. We're going to take a negative of that, so we actually get a value of 7. So it turns out that this function is a real special function. We call this the absolute value function, but this is the piecewise definition of that absolute value function. Sometimes a piecewise function will actually have more than 2 parts as well. So in this example, there's 3. And you might also be asked to graph them. So I want to do that here with you guys for this example. We're going to actually graph this piecewise function. So I'm going to draw a graph here, an xy plane, and I know that the cutoff point here is 2, so let's put in a value of 2, and let's use some colors. So the blue graph lives on the domain x less than 2, then we'll have a green graph for x equal to 2, and then let's make this 1 times x. We'll have a red graph if x is bigger than 2. Okay, so what we're going to do, for x less than 2, that means way over here, anything less than 2, it's going to be based on that blue, the blue function there. So you can go back to the algebra review for how to graph these things, but I'm gonna graph that for you. I know the y-intercept is 1, and it's got a negative slope, so it's gonna look like it's got a -1 slope. So it's gonna actually look like this. It'll be a line. And now since x is less than 2 for this blue, I'm going to put an open circle here, meaning that circle is not actually included on this blue line at 2. Because at 2, the graph has a value of 5. So now we have to go way up here to the value 5 and fill in a green circle way up here at the value of 5. And then finally for x bigger than 2, that's for all this stuff over here, it's going to, the graph will just be x. It doesn't really need the 1 there, of course. The graph's just going to be x. So, you know, at 2, it'll have a value of 2. So this is 1, 2, 3, 4, 5. So at 2, it'll have a value of 2. So we can put an open circle there at 2. And then it's going to have a positive 1 slope as it goes off to the right. So if I erase these things, what you have here is a graph of this piecewise function. Oftentimes you might be asked to find the domain of a piecewise function. It is a little bit tricky, and I'm going to kind of go through one example here that'll highlight a lot of the tricks associated with this. So the first step, when you look at the piecewise function, you have to look at how it's defined. So the first piece, the blue piece here, is defined on the domain from 1 to 5, and the red piece is defined for anything larger than 5. So again, I'm going to draw a number line just to kind of help me out here. Everything starts at 1. The blue, it lives in the blue function from 1 to 5, and then it lives in the red, by the red rule, from 5 and beyond. So I know that my domain, certainly nothing's happening over here, so to the left of 1, our function doesn't exist. But I want to make sure that there's no other problems that could happen. as we talked about with domain on a previous slide. So I'm going to look at this blue function. I'm going to just algebraically manipulate that a little bit by factoring the denominator. So when you factor the denominator, you're going to get x minus 4 times x plus 2. Again, you can check that and check out the algebra review if that's unfamiliar to you. And I see here that x cannot be 4 and x cannot be negative 2. So when I look at my domain, I know that at 4, I have to skip it. My function has to actually jump the value at 4. So what's going to happen is, if I'm going to shade this, I can have 1, and the blue function lives from here all the way to 4. It has to skip 4 because we have a problem there, and it's going to go all the way to 5. And then my red function takes over after 5. So when you actually look at it at the function as a whole, if we express the domain, we're going to go from 1 to 4. We have to skip 4 and go from 4 all the way to infinity. I don't have to stop at 5 because there's nothing I don't have to jump anything at 5. The blue seamlessly transitions to the red. So our domain will look like this. And last but not least, let's look at a few word problems. With piecewise functions, it's often important to be able to create the function for a particular situation. And here's one such situation. Suppose you have a car salesman. And you'll see one of these in your homework as well. But suppose you have a car salesman. He makes $400 a week, plus some commission that's based on the number of cars that he sells. And then it goes on to tell us that he makes $40 per car for the first 10 cars that he sells, and $75 per car for any car over 10 that he sells each week. So we're going to write a piecewise function that can be used to find his salary. What we're going to do to start is we're going to let x, so our variable, represent the number of cars that Jake sells. So x is actually just our number of cars. And now our salary, we're going to have that be our function f of x. And it's actually going to be a piecewise function because it depends on how many cars he sells. So if he sells less than or equal to 10 cars, we know that his salary is going to be his weekly salary, the $400, plus $40 times x, where x is the number of cars. So if he sells 5 cars, he's going to make his $400 plus $40 times those 5 cars. And that'll be valid all the way up until the 10th car. But if x is bigger than 10, so if he sells more than 10, he gets his $400 weekly salary. He gets $40 for the first 10 cars. So because he sold more than 10, he's going to get $40 times the number of cars, plus $75 for each additional car that he sells. So the way that we can express this, so this I need a little room here. This is for x bigger than 10. $75 times x minus 10. And why am I doing that? Well, let's say he sells 12 cars. Well, 10 of those cars get $40 commission, and 2 of the cars, so 12 minus 10, each additional car past 10 gets 75. So it'll be 2 times 75 and 10 times 40. And this is actually going to be his function that tells us what his salary is. So suppose he sold 20 cars, you would determine which branch of the piecewise function you need to go for. So that would be the red branch because 20 is bigger than 10. And you would input 20 into that formula and you could find his salary. So get a little bit of practice with this. Let me know if you have any questions. I'll see you in the next video.